So in this question here, I've got a parametric curve and x equals 3 sine squared 3t and y equals 2 cosec 4t. Now we want to find dy dx, i.e. the gradient of this parametric curve for any value of t. So let's have a look what we've got. So dy dx, that's what we need to find. Now we've got our x's and our y's here in terms of t. So the equivalent of this will be dy dt divided by dx dt. That's kind of our building blocks. So if we get our derivatives each and then set them up into a fraction, and then we'll be good to go. So let's have a look at this x first. So x equals 3 sine 3t, and then this is all squared. So I like to write things like this sometimes when I'm trying to do derivatives like this. So that is equivalent to that because it's sine squared of 3t. Okay, so now I can apply the chain rule here. So now my dx dt equals 3. Now by the chain rule I can bring this 2 out the front and multiply it. So now multiply that by 2. And then I've got sine 3t with the power dropped by 1, which is just sine 3t. So times sine 3t. Then I need to multiply by the derivative of what's inside this bracket, which is cosine 3t. Derivative of sine is cosine. So cosine 3t. And then by the chain rule, I need to multiply the derivative of inside this bracket. Derivative of 3t is just 3. So let's simplify this off now. So 3 times 2 times 3 is 18. And then I've got sine 3t cosine 3t. Now that would generally be good enough for a result, but I can do more here and turn this into one trig function. So what I can do is, if I just have a look at the sine sum formula, so sine of a plus b, that equals sine a cosine b plus sine b cosine a. Now what I could do is here, as I've got 3t and 3t, if I let a and b equal 3t together, I could then set this to a plus b, which would be sine 3t plus 3t. So sine, so let's just put that there in a box, sine 3t plus 3t, and that equals sine 3t cosine 3t plus sine 3t cosine 3t. So you notice now with these are the same. So here I've got sine of 6t equals 2 sine 3t cosine 3t. So as I've got 2 of those, just multiply them by 2. So then here I've got a sine 3t cosine 3t, if I just ignore this 18 for the moment, but sine 6t is 2 of those. So I can now set this to sine 6t. I put sine 6t, and as I've got 18 there, and this represents half of what I've got here, I can divide this by 2, and I've got 9 sine 6t. So that takes care of dx dt. Now let's have a look at dy dt. So I'll keep this sum formula inside a box here. Okay, so now dy dt. So y equals 2 cosec 4t. Now the derivative of cosec, that's going to be negative cosec times cotangent. So a dy dt, that equals 2. And as it's negative, I'll just write negative here rather than put it further along. Then I'll have cosec 4t, cotangent 4t, and then by the chain rule I need to multiply by this 4. So times that by 4. 4, not 8. 4 times 2 is going to give me 8. Okay, so that takes care of that. So now let's simplify this off. So now I've got negative 8 cosec 4t cotangent 4t. So that's my building blocks to put inside here. So dy dt. So let's just give myself a little bit of space. So this equals dy minus 8 cosec 4t. And then cotangent 4t. Divide all that by the 9 sine 6t. Okay, now that'd be good enough for answer, but I can do something with these cotangents and cosecs. So this is all in terms of 40, these are in terms of 60. So I can't combine any signs with this one. But I can keep my minus 8, that'll be fine. And I'll definitely have my 9 sine 6t there. Now cosec we know is 1 over sine. So let's write that here. Cosec 4t is 1 over sine 4t. So if I've got cosec 4t there, I can put sine 4t. And if I've got cotangent 4t, let's put that one there. Cotangent 4t, that equals cosine 4t over sine 4t. So I can put cosine 4t in my numerator. And then I've got another sine 4t I can put in my denominator. So instead of writing another one, I just multiply it by this one, and then it'll be squared. And then that will be my answer. So that will be my answer for my dy dx of this parametric equation. Okay.